Okay, let's dive right into this explainer and decode a seriously gripping 14-day engineering mystery that went down aboard the MV Sapphire. We are talking about a high-stakes detective story here. Not your typical crime scene, but one set deep inside the engine room of a massive vessel that's actively navigating the open ocean. We're going to trace exactly how the crew, along with the shore team, essentially hunted down a ghost in the machine. So, how do you find an invisible, high-pressure gas leak in a 300-bar marine engine while you're literally sailing across the ocean? Well, the crew of the Sapphire had to figure that out. And get this, they had to do it without tearing the running engine apart. Just imagine trying to find a microscopic puncture in a high-pressure system. The gas itself, completely invisible. The pressures, totally deadly. And shutting down the engine for more than an hour simply isn't an option because, again, you're actively sailing. It is a total engineering nightmare. But as we're going to see, human ingenuity is a pretty powerful thing.
Right, so here is our crime scene. As Master Captain Loken reported on February 14th, 2026, the main engine just flat out refused to run on gas. Basically, the second the main engine line pressure hit somewhere between 65 and 85 bar, the safety systems triggered a gas trip. Why? Because dangerous methane levels were building up. The ship's sensors were absolutely screaming that there was a leak somewhere, but nobody could see it. Tracing how this whole thing unfolded really connects the crisis back to an earlier event. Notice that back in September 2025, several engine units, specifically units 1, 2, and 3, had their control and adapter blocks overhauled. Now, months go by, everything seems totally fine, no apparent issues at all. Then, out of nowhere on February 14th, the gas trips begin. Initially, the crew found some scratches on two specific valves, 801 and 818, and they polished them up. Case closed, right? Nope. By February 15th, the trips were still happening across other units, which actually prompted the shore-based technical team to step in on the 16th.
All right, Section 1, initial tests and false leads. Let's get into it.
Like any good detective story, the engineers started with the obvious suspects and the standard interrogation methods. This part brilliantly highlights the utter confusion the crew was facing early on. First, they tried a flange bubble test. They pressurized the system to a massive 250 bar with nitrogen, lathered soapy water on the exterior, and literally nothing. A completely perfect seal. But the pressure drop test told a completely different story. They pumped it up to 153 bar, walked away, and just 1 hour later, it had dropped down to 143.1 bar. So the bubble test proved there were zero external leaks, but that pressure drop absolutely confirmed that the gas was hiding and leaking somewhere deep inside that complex engine infrastructure. Here's the real kicker. They are hunting this ghost while totally handcuffed by some massive operational constraints. The vessel is actively sailing on traditional, very low sulfur fuel oil, which means the engine is firing, it's vibrating, the whole shebang. They literally cannot stop the engine for more than 60 minutes. On top of that, just to manually open or close the test valves, the hydraulic oil pumps have to stay running. And maybe the worst part? The safety ventilation fans, the double wall fans, are creating such a strong vacuum that they're actually tripping the gas detectors and messing with the testing. Moving on to Section 2, the double wall pipe mystery. Okay, so if the leak isn't on the outside, it absolutely must be trapped somewhere within the complex double wall pipe network that spans across 7 different cylinders. To find this invisible nitrogen gas they were pumping in for testing, the crew came up with a really clever plan to measure oxygen displacement. The logic here is that if nitrogen was leaking into those double-walled pipes, it would physically push the normal, breathable oxygen out of the way. So they purged the line with fresh air, turned off that problematic ventilation fan, pressurized the line with 50 bar with nitrogen, and then literally went around manually sniffing the outer pipe plugs to check for drops in oxygen levels. They were mapping out exactly where the nitrogen was pooling. And the results of that test? Absolute smoking gun. Normal breathable air is about 20.9% oxygen, but the readings near units 2 and 3, the oxygen plummeted to 7.5% and even as low as 5.9%. I mean, that is a huge drop. That tells us the space was almost entirely flooded with the nitrogen they were using for the test. The leak had to be isolated right in that specific zone. Chief Engineer Krivoshea Oleg brilliantly connected this massive oxygen drop right back to that timeline we talked about earlier. Remember September 2025? Well, the massive leak was occurring right where those overhauls took place. The puzzle pieces were finally really starting to snap together. I actually want to pause on this number for a second. 50 bar. The crew noted in their communications that just 50 bar of nitrogen pressure was enough to completely displace the oxygen in those pipes. To put that into perspective, that proved they had an absolutely massive internal leak on their hands. We are not talking about a tiny pinhole here.
Okay, Section 3, Interrogating the Purge Block. Noting those test results, along with a secondary leak signature near Cylinder 7, the shore technical team directed the ship to interrogate a highly complex component known as the purge block. Now we have our lineup of suspects. Pneumatic valves 806, 808, 809, and 820. The technical team on shore wants the crew to test every single one of them. But there is a huge problem. The ship has absolutely zero spare spindles for valves 809 or 820. If they take them apart and accidentally break them, the ship's gas systems are completely dead in the water. Talk about high stakes.
So, they begin carefully manipulating the valves to see exactly which one is betraying them. When they opened valves 806 and 808, but kept 809 shut, the pressure violently jumped across the diagnostic ports. Port D3, for instance, spiked all the way up to 4.9 bar. The internal seals were clearly failing under the shifting pressures, allowing gas to escape exactly where it shouldn't be. Talk about a frustrating day at the office, right? The crew completely overhauled valve 809, and it passed perfectly on the workbench. But the second they put it back in the engine, it leaked immediately. On top of that, valve 820 was completely losing its non-return functionality. They tried a new welded part for 820, and that refused to seal too. And perhaps the wildest, most unbelievable detail in this entire thread, they tried to do a simple soapy water bubble test on the block, but the leak was so violently strong that it literally blew the water away before bubbles could even form. Just crazy. All right, Section 4, Final Isolation Sequence. Desperate for some clarity here, the management company actually called in the original makers, Everlance, to provide a foolproof isolation sequence. This sequence brilliantly builds a logical trap. It's an incredibly elegant process of elimination for an impossibly complex mechanical maze. Step by step, they open one specific valve, let the nitrogen flow, and then check a very specific diagnostic port. For example, if nitrogen leaks from port D4 under a specific lineup, you know for a fact valve 809 is your culprit. But even with this trap perfectly set, valve 820 kept refusing to seal. And remember, they had no spare parts left whatsoever. So Pratik Tiwari from the shore technical team proposes what is basically the nuclear option. If the valve won't seal, forcefully alter its very nature. The instruction was to blind off the valve. Basically, blinding off is a mechanical engineering tactic where you permanently seal a passage. By welding a slotted screw in there, they turned a complex, failing non-return mechanism into a simple open block. This effectively removes the malfunctioning component from the equation entirely. It allowed them to finally complete the tightness test and restore temporary operational integrity to the rest of the system. It is a total brute force, highly resourceful fix born out of pure, absolute necessity. It's just a fascinating conclusion. It really shows that no matter how complex the technology gets, we're talking massive 300-bar engines, double-wall ventilation pipes, high-tech methane sensors, sometimes you just need incredible human persistence, solid logical troubleshooting, and, well, a single welded screw to save the day. So I'm going to leave you with this question to think about. When a multi-million-dollar vessel's efficiency hangs on a single, improvised mechanical fix, how far would you push your troubleshooting to solve the mystery? Thanks for joining me on this explainer, and keep questioning how the world around us works.